Today, let's talk about electrical resistance. In our recent lectures, we've talked about a property of conductors called conductivity. Now remember, conductivity is the measure of the ability of a material to conduct an electric current when exposed to an electric field. We had seen conductivity arise when we had an expression relating current density to electric field. And we see that the conductivity is the proportionality constant of the electric field to the current density. The larger the conductivity, the larger the current density for a given electric field. The smaller the conductivity, the smaller the current density for a given electric field. So it's very useful to look at things in the context of conductivity. However, what is often very useful to think about is the measure of a material's ability to resist electric current when exposed to an electric field. And that's what we're going to call resistance. To think about resistance, I want you to think about a ball rolling down an inclined plane where there are a bunch of pegs in the way. The motion of a ball rolling down an inclined plane and bouncing off pegs in its path is analogous to the motion of an electron in a metallic conductor with an electric field present. If the pegs were rearranged or if some were removed, the ball would experience less resistance to its movement. If more pegs were added, the ball might experience more resistance to its downhill motion. So remember, as a charge moves through a conductor, it's having numerous thermal collisions. It's bouncing against other charges. It's bouncing against other particles in the conductor. And in order to keep that particle moving, we need to establish a potential difference. Now, think of that potential difference like a hill. Think of a circuit in which we have a battery maintaining a potential difference between 2 points in the circuit. Let's use the analogy of a hill or a plane to represent the potential difference. The height of the plane, or the angle it makes above the ground, will represent the value of the potential difference. The steeper the plane, the greater the potential difference. The more shallow the plane, the smaller the potential difference. Now imagine that we position a charge carrier at the top of this plane. We'll say this is a positive charge. If we place the same positive charge on each of these two planes, the plane that is steeper will cause that charged particle to move down quicker. So here we could see that the potential difference using this analogy is directly, or the current rather, is directly proportional to the potential difference. The larger the potential difference, the faster our ball will be moving by the time it gets to the bottom of the plane. Now imagine there's some barriers to its motion. So I'll try and put some three-dimensional perspective to these planes. So if there's some barriers to its motion, a bunch of pegs that are going to inhibit the motion of our charge carriers as it moves down the plane. So this charge carrier will go down, will hit a peg, hit another one, bounce there. Sometimes it'll pass right through. If you position it slightly in a slightly different location, it'll bounce from peg to peg, eventually get through. So if we had the same pegs, for example, on the plane that was shallower, so in other words, a smaller potential difference, this charge would take a long time or much longer to get through. And that's because there are barriers to its motion. If we want the charge or more of the charge to get through quicker, we have to increase the potential difference. So in other words, we have to elevate our plane. Similarly, this idea of resistance is similar to the idea of rolling a ball down a plane. Notice how the ability to carry a certain amount of current depends on how much potential difference we apply. With this said, let's define resistance. Resistance is defined as the ratio of potential difference across a conductor to the current that it carries. So here, for a given amount of current, if it takes a certain amount of potential difference to maintain a certain amount of current, then we say that our resistance is that ratio of potential difference to current. If we need more potential difference to carry a certain amount of current, then the resistance is higher. If we need less potential difference to carry the same amount of current, then the resistance is lower. Now here, the units of resistance we call the ohm. We use the Greek letter omega to represent ohm. And 1 ohm is equivalent to 1 volt per amp. So in other words, the potential difference per current. It can be shown that the resistance in a conductor depends on the size, shape, and resistivity of the conductor, given by this Greek letter rho, which we are going to use to represent the resistivity of the conductor, times L, the distance in which the charge carrier moves through the conductor, divided by A, the cross-sectional area through which a charge carrier moves. So here we see that resistance is directly proportional to the length of the conductor and inversely proportional to its cross-sectional area. So let's begin by kind of sketching what we mean. Let's say we have a conductor of a certain length. This conductor is of length L and cross-sectional area A. It is through this cross-sectional area that our charge carriers move through the conductor. Now, even though I'm depicting this motion in a straight line, that is just the net motion. Remember, each of these charge carriers undergoes random collisions in the conductor. So it's not really taking a straight line path, but on average, it's moving in a particular direction, which happens to be opposite the direction of the electric field established in the conductor if our charge carriers are negative charges, as they are in the conductors that we work with in the everyday world, like copper. Remember, negative charges will move from low potential to high potential. So the low potential side is on this side, the high potential side is on this side, and therefore this conductor, the potential difference establishes the electric field, and we know there is a relationship between the electric field and the potential difference established in a conductor. We've shown previously that for a uniform electric field, the potential difference is equal to the magnitude of the electric field times the distance between 2 points in our electric field. So the potential difference from one end of this wire to the other end is equal to the magnitude of the electric field in the wire, which we know, being a conductor, in electrodynamics, the electric field in conductors is uniform, so constant in magnitude. And so the potential difference is this electric field times the distance through which that 2 points are in this conductor, represented by the length of this segment of wire. Let's use this information to show that the resistance in this wire is directly proportional to the length of the wire over the area, where the proportionality constant is Rho, the resistivity of the conductor. Let's begin this proof by starting off with the definition of resistance. Resistance is defined as potential difference per current. In other words, how much potential difference do we need to establish a certain amount of current? Now, we know that potential difference in this conductor is equal to the product of the electric field times the length, so the distance between 2 points in this conductor. And the current can be expressed in terms of current density and cross-sectional area. Remember, current density was defined as current per unit area, which means current can be defined in terms of current density and area. So here then we have that the resistance of this conductor, of this segment of conductor, is equal to the product of the electric field and the length of the conductor over the product of the current density and the cross-sectional area through which our charge carriers move. Well, remember, current density is directly proportional to the electric field, where the proportionality constant we call the conductivity. So this means we could write resistance is equal to the ratio of the product of the electric field and the length of the conductor through which the charge carriers move over the conductivity times the same electric field times the cross-sectional area. Notice that the electric field in the numerator cancels with an electric field in the denominator. This gives us that resistance is equal to 1 over the conductivity times the ratio of the length of our conductor over its cross-sectional area. Look at what we have here. This quantity right here, 1 over the conductivity, let's define that as Rho, resistivity. So we could say that resistivity is defined as 1 over the conductivity. Now that makes sense. If something has a very large conductivity, that means the resistivity, its resistance to the flow of charge, is small. And if something has a very small conductivity, then its resistance to this flow of charge is large. So with this definition for resistivity, we have now shown that the resistance in a conductor of length L and cross-sectional area A is equal to the resistivity of our conductor times the ratio of the length of our conductor over the cross-sectional area.